Welcome back everyone, and we're looking back at our logarithms and log laws. You'll notice here that for the bases I've just put in b, and you'll notice that they're all the same bases, and that's what makes these log laws work. So here for instance log is log base b. If it was a base of 10 it would just say log. If it was a base of e we'd be using ln. And the log itself is then a product of two unknown variables. It doesn't matter what they are in this case, we're just demonstrating the rule, and we'll be like that through this video. So this is equal then to a log with that same base, x plus. So the multiplication essentially we could say becomes a plus, a log with the same base, y. Right, so to put that into like a little demo, and the way we would actually use this is kind of backwards, because we would see a situation where it might say something like log, and the base is x this time, 14, and we see plus another log with the same base, which would be x, and that can just be a. We'd be able to put that together and essentially simplify it as much as possible into a log with the same base, remembering that that base is then x, and it would be 14a, the product of those two values. Where we see added logs with the same base, they become one log with that same base, and it will be the product of the two logs. To move to our second law, briefly here, we see once again we have logs with the same base running throughout, but this time it is, we can say a fraction, but it's a division there. Here we might sometimes write that poorly as log base b, and we could say x divided by y. You know, it doesn't look as good, it's not as algebraically neat and correct, so we're going to leave it this way, log base b, x over y, where that is the entire log. And the rule here is that they are then minused. So to again write it kind of the other way, the way we may see it in a question or in our activities or exams, obviously in a more complex situation, let's go with a log, just log. It's a base 10 this time, let's say, and we see a log a, and it is minus, in this case log, it's the same base 10, so we don't write it. B, we'd simply be able to say that that is log a over b. Nice and neat. You know, something like this becomes useful when we can start applying our last two laws that we're going to look at. We call them deductions sometimes. And we can simplify these logs further when the log itself begins to interact with the base. The values are the same, or the values are 0 or something like that. But we'll see that at the end of this short video. So have a look at this one. This time we're interested in this exponent. All right, so let me put a little red circle around it here. That's the exponent that we're interested in. And notice that it appears here. Now, it doesn't particularly matter that the bases are the same throughout, because really what we're worried about is moving this exponent to the beginning of this log. So you'll see the n moves from there round to back here. So that is n log bx. And whatever the log base and logarithm are doesn't matter. We're just moving that exponent. So I mean, this could be a case of, you know, it could be a log base 2 like that, and this could be a x, you know, to the power of pi or something, and we'll be able to simplify that through by saying pi log base 2, and this becomes useful with this law down here. Okay, so our kind of fourth law, sometimes in the textbooks you'll notice they separate that out, and they'll say this is a deduction, not a law. However you want to describe it. If you have a base and a log that are the same, we get 1. And there's a couple of ways that this is useful. If we look up at our example we just looked at now, for instance, if I had a case where it was log base 2, and say that was 4, we would be able to say that that is equal then to log base 2 squared, because the 4 can become 2 squared. Then we'd be able to put that 2 at the beginning, so it would be 2 log 2, base 2 to the 2, and that log base 2 to the 2 would equal 1, so it would end up, because of this law, we would end up with 2 times 1, which would equal 2. Nice and simple at the end of the day. So log base 2 to the power of 4, we can simplify it right down to 2, which we couldn't do without applying these rules. The last thing that we can do here, there's another law to come. When I say last thing, I mean with this particular log. What is interesting here is if we rewrite the log, remembering that this x here is the base. So if we were to rewrite this in exponent form, the base is, the x. The equal to part is the index of that base, so it's to the power of 1, and it would equal the logarithm, so it would equal x in this case. So if I were to kind of maybe add a little color here, that's our base in red, and then here our log in blue goes over there, and our exponent, okay, I'm going to have to leave it black, I'm out of colors, is number 1 over there. And we know from our exponent laws that anything to the power of 1 remains the same. So it makes sense in this case, no matter what it is, if it is log base 2, it equals 1. If it is log base pi, it equals 1. Right. A very useful law there. The last one that we're going to look at is this one here, where log base x, 1, and it doesn't matter here what the base is, the idea is that the log is 1, is equal to 0. And this is really a simple little log law. And you can imagine us trying to simplify down to this situation so that we can just remove a term. Now we'll have some examples coming up in future videos where we'll use this law like that. But once again, we can say with the base x to the power of 0 is equal to 1 if we rearrange this, which from our exponent laws we also know to be true. So we're really just rearranging this into a logarithmic form. All right, thank you very much for watching. There will be more examples of these worked examples to come soon, so have a look out for those. Thanks.